Today I'm going to be talking about carbon monoxide and how it is a potent inhibitor of cytochrome C oxidase. Cytochrome C oxidase is an important component of the electron transport chain. It's also known as complex 4. Cytochrome C oxidase is important in catalyzing the reduction of O2 to form water. And it is coupled to the pumping of 4 protons back into the inner membrane space, which provides the proton gradient ATP synthase needs to produce ATP. So a little bit about cytochrome C oxidase. It is located in the mitochondrial inner membrane, and its active form, it's a dimeric protein and also a transmembrane protein. The redox centers involved in the electron transfer from cytochrome C to the active site are the two heme moieties A and A3 and the copper centers CoA and CuB. And these 3 subunits I included in this photo are actually encoded in the mitochondrial DNA and are synthesized in the mitochondria. And subunit 1 is the binuclear center where oxygen is held, and subunit 2 is the primary electron receptor region from cytochrome C. And I thought it was interesting that magnesium and a magnesium ion stabilizes the interface between subunit 1 and 2. Looking at the electron flow, electrons are initially donated from cytochrome C one by one. They're transferred through the complex by copper ions and hemes, as you can see in the picture. And cytochrome C oxidase actually holds onto oxygen at a bimetallic center. And this is because until it collects 4 electrons, it exists as a radical, which can impact mitochondrial function. 4 protons and 4 electrons are consumed in this process to form water, and in response, it is coupled to 4 protons exiting the matrix back into the inner membrane space, so ATP synthase can have the proton gradient it needs to function, so to take ADP and PI and form ATP. Carbon monoxide actually is a potent inhibitor at the cytochrome C oxidase level, and this is why. So first off, carbon monoxide is a tasteless, colorless, odorless gas that results from the incomplete combustion of fuels, carbon-containing fuels. Most notably, motor vehicles using domestic gas for cooking or heating can emit carbon monoxide, charcoal and wood fires, and tobacco smoke. We care about carbon monoxide poisoning because it affects 50,000 people per year and has a 1 to 3% mortality rate. We also care because people are exposed to carbon monoxide daily, even I am, most people who drive cars. Its neurocognitive effects with long-term exposure are last long-term in about 15 to 40% of people. There is no antidotal therapy for carbon monoxide poisoning. It is limited to just getting out of that environment and hyperbaric oxygen in locations where that is available. So, as previously stated, carbon monoxide inhibits cytochrome C oxidase. And this is because if we go back to subunit 2, that is the primary electron acceptor region. And at this region, carbon monoxide binds very tightly to iron in the heme A3 and subunit 2. So it prevents oxidative phosphorylation as a whole, and it inhibits the reduction of O2 to water. And by this, the transfer of protons in the inner membrane space doesn't occur. I wouldn't say it shuts down ATP generation through ATP synthase, but it greatly reduces it. And it can accumulate electrons entering the electron transport chain through complexes 1 and 3, which produces superoxides and free radicals. Just because cytochrome C oxidase can be partly inhibited doesn't mean that electrons aren't still shuttled through the chain, which can accumulate these free radicals, and that leads to decreased mitochondrial function. And it should also be noticed that CO can actually bind to hemoglobin, and does with a lot, has a higher binding affinity to hemoglobin than O2, which can reduce total oxygen carrying capacity by hemoglobin. Obviously, preferentially binds CO instead of O2, and this has to do with hydrogen back bonding. And it also stabilizes the quaternary state of hemoglobin, which binds with to O2 with higher affinity and will not release in a low VO2 environment. So overall, carbon monoxide prevents the reduction of O2 to water, and the coupled reactions that remain give this proton gradient, maintain this proton gradient, are no longer there, and ATP synthase has no gradient to use as energy, or cannot harness energy to make ATP. Thanks for listening. Have a good break.